So I think maybe another wrap-up of like a quick wrap-up of the previous one protocol gives a map.
Okay.
It definitely helped me. So.
Yeah. Okay, so for the protocol gives a map.
Can you explain what's the, I couldn't understand what's the algorithm. What was the purpose of the algorithm? Why did it do?
So the idea is that if I can, I'm given a read-write protocol for some problem. And protocol is just a piece of code. And what I really want to show is that if I have this algorithm, then I can construct a simplicial map from some chromatic subdivision of the input complex to the output complex that basically agrees with the problem specification. So given a protocol, the protocol is a program that runs in time, has inputs and outputs. And I want to turn this into just a static mathematical object, which is a simplicial complex with a map.
What do you mean that the participants in the protocol would draw somehow the complex, or that the output complex will be the divided complex? What do you mean by complex?
Well, so one way that I could do this is I could just say, okay, so here is the protocol complex for the read-write protocol. And here is the chromatic subdivision, and I could write down what the map is, but that would be very complicated and be hard to understand. So instead, what I'm going to say is, well, if I take this, you can take this chromatic subdivision and just think of it as this very simple iterated full information algorithm, where I read information, I write something, I take an immediate snapshot.
What do you mean that the output of the output complex of the protocol will be the divided complex?
Yes. Yeah.
Okay.
Yeah. So I have the simple iterated protocol whose protocol complex is this repeated chromatic subdivision. So
you design some complex like this, and why does it show that
Yeah.
the map?
Yeah, so I start out with this read-write protocol.
I think a simpler way is if somehow magically, so you are given a protocol. If somehow magically the protocol is already given as an iterated immediate snapshot protocol, then clearly the theorem, the map is obvious because you take the iterated immediate snapshot subdivision, and that's your map, and map down. Use the output mapping.
What is the
I mean, if you happen somehow, magically, you have a protocol that is based on immediate snapshots, on iterated immediate snapshots, then this direction is also simple, kind of.
Yes.
Because if it's immediate snapshot, you know how to construct it.
Yeah.
It's a chromatic subdivision.
Yeah. So then it looks looks like that.
This is what it is.
Yeah. And if you do it once with one piece of memory and you move on and use a clean piece of memory, then it's it's the same thing again and again. And
So now all you are left is if you weren't lucky to get an immediate snapshot, protocol based on immediate snapshots, and that's why what you do is simulate.
But can you say that there is a simulation, right, to prove that? Or this is what you prove now?
Yeah. So what I prove now is that there is a simulation, so that no matter what your read-write protocol does, I can simulate it in this very simple form of doing the repeated immediate snapshot. And so the way I do this is I run the repeated immediate snapshot, and on the side, I do the simulation. And basically, the simulation says that I have this vector of simulated memories, and so does everyone else. I read their vectors, I put everything together, I do some arithmetic, and if the arithmetic works out right, then I say, oh, I've just simulated a snapshot, and then I write a new value out in the simulated state. And so in the end, what you end up with is I have this very regular iterated immediate snapshot protocol, and I have this possibly somewhat irregular computation that I'm simulating on the side. And then as I run one protocol, I simulate the other one on the side, and then what I end up with are the two equivalent states. And then if I go back and say, well, this is a vertex of a complex and that's a vertex of a complex, then the simulation gives me a map from one to the other. Because any execution over here will give each process only one vertex over there. And then you have to argue that, in fact, it works.
Well, by the way, you say there is a problem with the color task, that it should be, the division should respect colors?
Yeah.
So where does it come?
So the way that this would, if you try to use the colorless algorithm, then what happens is, if you follow all of the same steps, then I can run this. Basically, you run a protocol where everybody converges on a simplex in the output complex, but you might end up on a vertex of the wrong color. In other words, that I might decide your value and you might decide my value. So for colorless tasks, we don't care, because it's, by definition, that's correct. And so that makes things much easier. The reason we do colorless tasks first is because it's much simpler.
And how do you take care here of the fact that it's
So here we had to do, when we do the simulation, you're simulating your own behavior. So that guarantees that it's color preserving, because I'm simulating my own behavior in the read-write protocol.
So in manifolds, it's the same for, if it is a manifold, it's the same for colorless and not colorless?
No, but manifolds are, no, manifolds is different from manifolds too.
For manifolds,
Yeah, so manifolds make colorless tasks easier. So colored tasks are harder than colorless tasks, which are harder than manifold tasks. And so during the whole course, we were sneaking up on more difficult things by doing the easier things first. But colored tasks that are manifolds are still harder than colorless tasks, because the fact that it's colored means that there's an asymmetry. That what's okay for me is not okay for you, and vice versa. So we have to be much more careful about doing our bookkeeping. Whereas before, we didn't have to worry about this. Now, there's an interesting open question, actually, is this the most elegant way to write that theorem? So another way so the colorless task, we said, well, there's a continuous map that approximates our task description. And so another way to do this is to say, well, for colored, there's a continuous map plus some condition. And intuitively, that condition is that you can't collapse large areas into small pieces. But I haven't been able to find a really satisfying way of writing that down. But I'm convinced that there is some simple property that would work. So that would be a really cool result, is if you could reformulate this theorem in terms of continuous map plus additional condition. And that would fit in much more nicely with the earlier version. But that would be a great conference paper. And probably a bad homework problem. Okay, so now I'm going to go in the other direction. So I'm going to say that suppose I have a subdivision, and now I want to create a map. And so I want to give you an explicit, I have a map and I want to give you a protocol. And so that means I have to give you an explicit protocol. So here we have our task. So here's our input complex, not to be taken literally. And here's our output complex. And what the task specification says is that for any input simplex, sigma, delta maps it onto a complex over here. Now this is a colored task. So we have red, green, and blue on both sides here. And so I'm given a chromatic simplex sigma. Chromatic just means that I have a distinct color at each vertex. I have a chromatic subdivision. Remember, chromatic subdivision just says that every simplex here that's subdivided is subdivided into pieces that have the same color. Every simplex here has distinct colors, and this red and green edge is is given only red and green colors in its subdivision. So I'm going to have an arbitrary chromatic subdivision, which I'll write div sigma. And so the what I want to prove, right, is that if there is a chromatic subdivision of sigma, and I'm not saying anything about what it looks like, any chromatic subdivision, and a simplicial map C, which is carried by a big delta, then there's a wait-free read-write protocol. So I'm given a subdivision here, I'm given this a map, and I wanted to get a protocol out of it. Okay, so could start with a special case. So suppose I'm given a simplicial map. Suppose the chromatic subdivision I'm given is just the iterated standard chromatic subdivision. So guess what we're going to do? Well, in that case, clearly there's a wait-free read-write protocol, which is just the one that I showed you before, where you do an immediate snapshot. You have an array of immediate snapshot memories, and you go through. We know we can do immediate snapshot with read-write memory because I showed you how to do that. We know we can do snapshot with read-write memory because I think Hagit's class probably talked about it. So that gives us, so in this special case, there's no problem. So and the protocol is iterated immediate snapshot. Everybody starts out on the vertexes of a simplex. We look at the chromatic subdivision, and eventually they all converge on some piece of that, and then we're done. So what we really want to show is that given any arbitrary chromatic subdivision over here, we can find an n such that the iterated standard immediate snapshot subdivision, that there is a color and carrier preserving simplicial map that goes from here to there. So it's color preserving in the sense that it sends each vertex here to a vertex of the same color over there. Carrier preserving says that if it's along this edge here, then it's going to end up along that edge there, and so on. So basically that says that's very similar to the statement that we had before, where you can simulate any arbitrary read-write computation with the iterated snapshots, except that now we're talking only about subdivisions and not about algorithms. So first I need to give you a geometric construction for the standard chromatic subdivision. So you may remember that in the very early parts of the class I gave you a combinatorial definition talking about partial orders on faces and so on. But now we really need to roll up our sleeves and pick particular points. So we'll do this inductively. So inductively, I assume that we have a way of geometrically representing each of the faces in a dimension n-1. And so what I'm going to do is I'm going to go to the barycenter of this triangle. And we're talking about geometric triangles here. So the barycenter is meaningful. And then I'm going to push off in each direction here. I'm going to push this yellow away from that yellow corner, this blue away from that blue corner by some small amount. And then fill in the basically put cones over everything here. And so the course notes have all of the epsilon delta details and so on, which I won't go over because I'm sure you can figure it out. But all that says is that the drawings of the standard chromatic subdivision that I've been showing you are how you would actually embed it in a space. Now, we'll define the mesh of the chromatic subdivision to be the maximum diameter of any simplex. And so with simplexes, actually the diameter turns out to be the longest edge. So what we do is we look at the longest edge of any simplex in the subdivision and define that as the mesh. So there's a basic fact, which is if you take this chromatic subdivision and you look at the mesh of the subdivision is less than some constant times the mesh of the original simplex. For some C, that's between 0 and 1. Some non-zero C. And exactly what that is, C depends on n. It's roughly n over n plus 1. And it depends on how far you perturb these things. But none of this matters as long as you have this C greater than 0 and larger than 1. So later on, we'll come back and explain why this choice of C might be important if we're worried about complexity. But as far as correctness goes, any value will do.
Can you say just equal?
No, we don't want it to be equal to 1.
No, equal to C times mesh. The mesh.
Oh, yeah, it could be equal. Yeah, should be equal. It could be less than 2. That's even better. But
sigma itself doesn't have to be equilateral. Sigma itself might have some long edges, and some short edges. So you can generally say it's
So given a complex, we'll define an open cover to be just a set of open sets that cover it. So a set of open sets of Euclidean space that contain the complex that we're looking at. So now we're talking kind of elementary point set topology. Now there's a theorem that if your complex is compact, which it is, finite and enclosed, then there's a quantity called the Lebesgue number, which has the property that if any set whose diameter is less than the Lebesgue number lambda lies entirely in one of these open sets. And this is a standard theorem of point set topology. So if you have an open cover, you're closed and bounded, which all our complexes are, then if you take any set whose diameter is less than lambda, then it's completely contained in one of these open sets. Now, the particular open cover we care about are what's called open stars of a complex. So here we have the open star is the set of simplexes that contain the vertex, but not including the what's called the link, that is the edges around it. So it's the interior of all of these triangles in this case. And you can see that these open sets cover everything. Any point in this polyhedron lies inside of one of these things. Now there's a lemma. Again, I'm not going to prove it, but you can figure it out for yourself. It's actually another good homework problem. Is that if I have two vertices lie on an edge, if and only if their open stars intersect. And this is true in general. If I have k vertices, they form a simplex if and only if their open stars intersect.
How do the open stars cover the edges?
The open star of this, say, includes the edge here.
Okay.
So if you're here, then you're in the open star of this guy and in the open star of that guy. If you're here, then you're in the open star of only of this.
Yeah.
Okay, so what we'll do is pick n large enough. So the closed star is basically the closure of the open star. It includes all of the sort of opposite edges. So we can pick n large enough. So as we keep doing this subdivision, remember the mesh is multiplied by some c, positive c less than 1. So if we do this enough times, we can get the mesh down to any small positive value that we want. So we do this enough so that the closed star of the subdivision has diameter less than the Lebesgue number. And so, here is the arbitrary subdivision that we're interested in. This is our chromatic subdivision. So it says that each star, each closed star of the iterated chromatic subdivision lies in some open star of div sigma. And we can use that to define a simplicial map. So I take a vertex, look at a closed star. I know it lives inside the open star of some vertex in div. Think of these as being two subdivisions of the same geometric triangle. And so I can just arbitrarily, pick, if there's more than one here, I can pick one arbitrarily.
This is not necessarily color.
No, no. That's that'll be the trick. So you can use the intersection lemma to make sure that this is, in fact, a simplicial map. So, if one vertex gets sent over here and one vertex gets sent over here, then the intersection lemma, about the open stars, if and only if the open stars are not empty, guarantees that this is, in fact, a simplicial map. And again, I'm not going to do this here, but the course notes have the details. And so what we've just proved is the simplicial approximation theorem, which we've used several times early on. So it says that, I have two subdivisions, this is actually a special case. I have two subdivisions of a triangle, arbitrary one and some iterated standard chromatic one. And what I've shown you is that there's a carrier preserving simplicial map that goes from here to there for large enough n. And I'm being very vague about what the large enough means. But it's not necessarily color preserving. That's the, that's what makes this thing interesting. The proof of the simplicial approximation theorem you can pull out of any undergraduate textbook, But we redid it here because I'm going to take the same proof and give it a few twists. So we'll say that an open star covering is chromatic if each simplex tau of the iterated chromatic subdivision is covered by open stars of the same colors. So here, this red and yellow colored simplex lies in the open star of a yellow simplex and a red simplex. So this is good. So this covering here is chromatic. If we were to make that blue, then it would no longer be chromatic. Or, well, it might be, but... if the open star cover is chromatic, then the simplicial map is color preserving. And again, if you want a complete proof of this is in the course notes. I won't do that here. But basically, you do the same kind of argument. You use the intersection lemma to show that we know that you're in color inside. Every simplex is covered by simplexes of the right color. You push each vertex to a matching color, and the result is a simplicial map. So what we need to show is that if we have a covering, we can make it chromatic. So we always have such a covering, but it's not necessarily the case that it's a chromatic covering. So we need to argue that we can fix this. Now, how can this fail? Well, we'll say that two simplexes conflict if they have disjoint colors. This triangle has 3 colors and this edge has 2 colors. But their polyhedrons overlap. So this is a simplex of one subdivision. This is a simplex of a different subdivision. And we're in trouble here because they overlap, but their colors are disjoint. So if you're looking at open covers with the stars, then this is not a chromatic covering, because this doesn't lie inside the open star of a yellow simplex, for example. And so, again, it's straightforward to check that an open star cover is chromatic if and only if there are no conflicting simplexes. If there are conflicting simplexes, then it's fairly obvious that it's not chromatic, and the other way is actually pretty easy to do. So then the next step is to talk about how to eliminate conflicting simplexes. So this slide probably belongs earlier. So let me remind you what a carrier is. So here we have a big triangle and then a subdivision. And this is the standard chromatic subdivision, but it can be any subdivision. And we're talking about the carrier of a vertex is the smallest face of the big triangle that contains that vertex. So the carrier of the blue vertex in the corner here is itself. The carrier of the red vertex here is this edge here. And the carrier of this one is the internal, this is the entire triangle. So the key idea that we want is something that we'll call a perturbation. So I have a subdivision, and I want to take some point and I want to move it over by epsilon in such a way that I still have a subdivision. And here too, I'm going to give you the high-level ideas. I'm not going to go into the forest of epsilons and deltas and so on, and hyperplanes that you need to prove this. But it really is a straightforward exercise if you've ever taken an undergraduate point set class. So the first observation is that if I have an open star, then that must contain an epsilon ball for some epsilon around each vertex. That I can find some epsilon, which may be very small, depending on what the star looks like. The star is not necessarily convex, for example. But there's some epsilon ball that everything in the ball is inside the complex. That's step one. Okay, step two is slightly more complicated. It says that I can take this vertex and perturb it within some epsilon ball, maybe a smaller epsilon, that has the property that I still have a subdivision if I do this. And so the way to think about this is that, the danger of moving a vertex from here to there a little bit is that I might collapse one of these triangles. And so what you do is you look at, say, well, each of these triangles is basically, in this case, it's a line sitting in a plane. And so I have a point that's not on any of these planes. The complement of these planes is an open set. And so I can move this vertex around inside some epsilon ball without intersecting any of these planes because the complement's an open set. You can always perturb something within some epsilon inside an open set. So that says that there's some epsilon where I can move the vertex any place in that ball and still have a subdivision. So I have a lot of freedom to reach around and make small adjustments. But it has to be inside the carrier. So here, we'll go back to our conflicting, if I have two subdivisions of the same simplex, I can't guarantee there are no conflicting simplexes. But what I can do is I can perturb them so there aren't anymore. And that's the key to the entire argument. So here I have rho has q plus 1 colors, so it's a q-dimensional simplex. Tau has p plus 1 colors, so it's a p-dimensional simplex. And the reason they're conflicting is that they lie in the same hyperplane of dimension p plus q. So if you write these out in coordinates, then you only need p plus q plus 1 coordinates to capture the whole thing. So because they overlap, they're basically squashed into a smaller dimensional plane. So next observation is that, well, it must be the case that some vertex has a carrier of dimension p plus q plus 1 because there are p plus q plus 2 colors. So So remember, each corner of this vertex has a different color. And so you have to, in order to have a simplex with these colors, you have to have, at least one of them has to have a carrier dimension 3, and that has to have carrier dimension 2. So that means that everything is squashed into a small plane, but it has to live inside a big carrier to have so many colors. So then the next point to check is that, well, because the carrier of this vertex is big, there's an epsilon ball of high dimension with the property that I can move this vertex around within that epsilon ball to any point within that epsilon ball and still have a subdivision. It's like in PowerPoint, if you set up these polyhedrons and you move the vertex around, the lines will follow it. That's exactly the same thing. I should do an animation with this.
So this is, in fact, you're raising it up.
Yeah. So basically, I can lift it out of the hyperplane. And so now, we have a bigger hyperplane. And you do this inductively. You start with the smallest conflicting simplex, you perturb it, you move to the next one, and so on. And
We avoid the conflict
by perturbing the subdivision. Yeah.
Another dimension.
Yeah. So but once you lift this up, you're not introducing any new conflicts. So what happens is that one way of thinking about it is that if you have two subdivisions, then unless you're really, really unlucky, you'll be okay, and the coloring will be chromatic. The only way it can fail to be chromatic is if you pick the wrong place, exactly the wrong place, but that's not stable. And if you perturb it by a little bit, then it's a chromatic subdivision. Or conversely, if you have a chromatic subdivision, you can always perturb things a little bit, and it stays that way. Okay, so this is our algorithm. So you repeat the following until your star diameter is less than the Lebesgue number for the coloring. So we're going to keep doing the iterated chromatic subdivisions until the diameter of our subdivision is less than the Lebesgue number. So CH star is our perturbed, conflict-free subdivision. I'm going to do one more chromatic subdivision of that, which makes its mesh get smaller. Oops, I may have introduced a non-chromatic coloring because I was really unlucky and put a vertex exactly the wrong place. So then I perturb it to CH sub star so that the open star covering is chromatic again. And so at each round I have the CH of n has a chromatic covering, but it might not have shrunk below the Lebesgue number yet. But then if I keep doing it until we get to below the Lebesgue number, then now I have a chromatic covering where everything is below the Lebesgue number. And then by the previous theorem, we have a color and carrier preserving map. And so that's how that should be color and carrier preserving a simplicial map. So this is, so that's the argument. I mean, I've skipped over a lot of the details, but I think you can probably fill them in. So the basic idea is that we're given a arbitrary chromatic subdivision and a simplicial map that's carried by big delta. And what we've constructed is a map that goes from the iterated chromatic subdivision to the arbitrary subdivision. And and the algorithm is we do an iterated immediate snapshot here to converge on a vertex. We push it through, and that gives us a vertex here. And then we push it through again, and that gives us a vertex here. And because this is all carried by a big delta, that's a correct algorithm for our task description. And so that gives us the protocol. Okay, so what did we prove? Well, we said that we proved that this color task has a wavy read-write protocol if and only if there is a chromatic subdivision. Any chromatic subdivision will do, and a color-preserving simplicial map from the subdivision to the output complex carried by delta. So let me leave you with two interesting open questions. One is, as I said before, the colorless task we had continuous maps. And it would be so much cooler if I could say, well, this has a wait-free read-write protocol if and only if there's a continuous map from the polyhedron of I to the polyhedron of O that satisfies an additional property. You know, I think that would be more elegant than going to a simplicial maps and so on. But you know, I don't have a nice, succinct way of doing it. You know, every formulation I can come up with is basically exactly the same as saying this chromatic subdivision, except even worse. The other thing is, what about the complexity of this? So the complexity depends on the Lebesgue number. So the Lebesgue number, though, is not a combinatorial thing, it's a geometric thing. So the Lebesgue number of a complex depends on how it's embedded in space. So I can take the isomorphic complexes, embed them in different ways, and have different Lebesgue numbers. And so if you give me an embedding, I'll give you an algorithm. But that doesn't tell you very much about what's the optimal, you know, what's the inherent. You know, I can give you an arbitrarily bad embedding, which will give you an arbitrarily inefficient algorithm. But nobody knows how to go the other way around. You know, is there a nice way to characterize the complexity of this algorithm, which is, you know, probably related to the inverse of the Lebesgue number of a good embedding. But you know, nobody knows anything about the complexity of these problems. So I've given you an existential proof that an algorithm exists, but very little traction for figuring out what the complexity of that algorithm is, because there's too many. There exists kinds of things. So, but it's a little bit frustrating. It's not existential like in the probabilistic method where there's no hope of figuring out what it is. It's existential in a frustrating way where if only you could figure out the best Lebesgue number embedding kind of things. So I think that part is not entirely satisfactory. So next time we'll talk about the renaming problem, which curiously is a direct application of this, because there's some results that I won't have time to go through all the way, but basically you can prove that a problem that everyone thought was impossible was possible because you can show that there exists a chromatic subdivision. And the existence of this chromatic subdivision implies the existence of an algorithm, though nobody has any idea what the chromatic subdivision looks like or even what the algorithm looks like. So we have this tower of existential constructions. And there too, you could do a PhD thesis, I think, if you could figure that one out. Okay, next week.